Hi. Well, today we're going to be talking about section 3.7, optimization problems. This is the real-world reason why you'd want to find maximums and minimums, like what's the maximum profit, or what's the minimum surface area of an object so that I can maximize the volume and save my costs in production. So let's get started. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So the first thing we look at is what are we trying to optimize? In this case, we're trying to maximize the volume. So I need a volume equation. This is going to be my primary equation. They didn't give me any variables, so I have to make up my own. I know this is a square base on this box, so if this is x, then this is also x. Then I'll have to call this something different because it may not be a perfect cube. So x squared times h would be the volume, length times width times height. That's my primary equation. But I have two variables, so I need a secondary equation. So secondarily, I'm going to use the value that they gave me of 108 square inches, which is my surface area. Surface area of this box would be x squared for the base, but it's an open box, so there's no top, so I'm not going to have 2x squared. The front will be xh, the right side will be xh, the left side will be xh, and the back will be xh. So I'll have 4xh's, so I'm going to add that on. That's my surface area, and I know the surface area is 108. So I'll have 108 equals x squared plus 4xh. I'm going to solve that for h so I can substitute it into my primary equation. The purpose of your secondary equation is to incorporate the numbers from the problem and to reduce the number of variables in your primary equation. So if I subtract x squared, I'll have 108 minus x squared, and that will equal 4xh. Then I divide by 4x. So then I'll have h equals 108 minus x squared over 4x. That's my volume. Volume is x squared times h, and that's my h. So 108 minus x squared over 4x. Once I distribute that through and cancel things, reduce things, I'll have 27x minus x to the third over 4. That's the volume. That's what I'm trying to maximize. So my goal here is to take the derivative of it. But let's think about if we're looking for a relative maximum and minimum or absolute maximums and minimums. Look at the domain. We're talking about a feasible domain for x. What if this box was just totally a piece of cardboard laying on the ground? Okay, then x squared would use up all of that 108 square inches. So x would be the square root of 108. That's the highest that x could be. So we know x is going to be less than or equal to that value. What if there was no base and the whole right side was you used up the 108 square inches. So the x could be 0 and we would just have h, so we wouldn't even have distance this way. So h would just be 108 and we wouldn't have any x value. So those are extreme values. They don't make much sense because they don't even make a box. But those are our endpoints of our domain. So we have a closed interval, so we're going to be checking y values when we get done with taking the derivative and finding our critical points. So let's take the derivative of this. It's 27 minus 3x squared over 4. When you set that equal to 0, you're going to subtract 27. So we have negative 3x squared over 4 equals negative 27. And then we're going to divide by negative 3 or multiply by 4, whichever one you want to do first. I'm going to divide by negative 3, so x squared over 4 equals 9. Then multiply both sides by 4, so I get x squared equals 36. Take the square root, and we get x equals 6 and negative 6. But the negative 6 doesn't make any sense. It's not in our feasible domain. So this is our only critical number. That is the only place where we could possibly have a max or a min, except at the endpoints. So now what we want to do is plug our endpoints into the volume, plug that critical number into the volume, and calculate the volumes. So we're trying to find the y values. If you put 0 into the volume equation, this original equation, not the derivative, but the original equation, with x's you get 0. If you put 6 in, you get 108. And if you put in the square root of 108, you get 0 again. So obviously this is our max. Go back and reread the problem, make sure what we're looking for is maximum, so we're choosing the maximum. So the x value that gives us a maximum volume is 6, The question is asking for what dimensions will produce a box with maximum volume. So if you write 108 as your maximum, you've not answered the question. We want the dimensions. So it's a 6 by 6. These are inches. 6 inch by 6 inch by, and then we've got to figure out h. So go back to your equation here, when h is equal to 108 minus 6 squared over 4 times 6, which is going to be 3 inches. So that is the answer to the question. These are the dimensions that will produce a box with maximum volume. The problem-solving strategy that they give you in the book: number 1, assign variables to the given quantities and to those to be found. Number 2, write a primary equation for the quantity to be optimized. Number 3, reduce the primary equation to a single variable using that secondary equation, or using a secondary equation. Number 4, determine the domain of the primary equation. And number 5, determine the maximum or minimum using calculus. That means either use the y values if you have endpoints, or use the first derivative test or the second derivative test. Let's do one more example. We have 2 posts. One post is 12 feet high. The other is 28 feet high, and they stand 30 feet apart, so this total distance is 30. They are to be stayed, which means secured in place, by 2 wires. So these are the 2 wires. The wires are attached to a single stake, so the stake is here. The wires run from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So what are we trying to optimize? Wire, and the optimization we're looking for is the least amount of wire, so we're looking for a minimum. So we need an equation, our primary equation. We need an equation for the wire. So we better assign some variables. We've got the 12 and the 28, and here we know that's 30. So we put our stake here. The distance from the 12-foot post to some random place on the ground could be x. So then the distance from that stake to the other post has got to be 30 minus x. That way we avoid creating a new variable. Here these do have to be 2 different variables because we may not have equal distance on these wires. So we have y and z. So now we've got 3 variables. I want to minimize the least amount of wire. So w is my wire, so it's y plus z. I've got lots of variables, and I also want to incorporate this x in there somehow. So let's write equations for y based on x and z based on x so that we can have everything in terms of 1 variable. Looking at this right triangle, we can do the Pythagorean theorem. So my secondary equation, one of them, is x squared plus 12 squared equals y squared. If I take the square root of both sides, x squared plus, and 12 squared is 144. There's one of my secondary equations. Doing the same thing on the right side, 30 minus x squared plus 28 squared equals z squared. Simplifying and taking the square root, I get x squared minus 60x plus 1684. So now I have 2 secondary equations that are both in terms of x. So I can rewrite my primary equation. It equals y, which is x squared plus 144 under a square root, plus the square root of x squared minus 60x plus 1684. Can you add these 2 together? No, you cannot. If they're under individual square roots, they have to stay that way. So that's my wire, and it's an equation in 1 variable. So now I'm ready to talk about my feasible domain. What numbers would make sense for x? Well, the closest x could be to the 12-foot pole is right next to it, so that would be a 0. The farthest x could be from the 12-foot pole would be 30 feet. So there's my feasible domain. I have a closed interval, so I'm going to be checking y values. I can take the derivative of this wire equation. This is x squared plus 1/4 to the 1/2. So multiplying that 1/2 out in front, subtracting 1 from the exponent, and multiplying by the derivative of the inside, plus the derivative of this part, 1/2 times x squared minus 60x plus 1684 to the 1/2, negative 1/2, times the derivative of the inside, which is 2x minus 60. I'm going to simplify this a little bit. So my derivative, 1/2 and times 2x would just be x, and then over the square root of x squared plus 144, plus Here, this 1/2 times 2x minus 60 is going to leave me with x minus 30 on the top, and then a square root of x squared minus 60x plus 1684 in the bottom. I want to set that equal to 0, so I better get a common denominator. So multiplying the left side by the square root of x squared minus 60x plus 1684, and the x minus 30 times the square root of x squared plus 144. And that's all over the combination of x squared plus 144 under a square root times the square root of x squared minus 60x plus 1684. So if I want that equal to 0, I want to simplify this a little bit. Just focus on that part. We'll have, I'll write it over here, x times the x squared minus 60x plus 1684 equals, and then I'm going to subtract this, so I'll have a negative, and then x minus 30, and then the square root of x squared plus 144. Okay, I'm going to finish that a little bit later. Let's focus on the denominator. Where would that be undefined? Is there any values that would make this equal 0? Well, if you square something and you add 144 to it, that will never equal 0, because you square something, it's positive. So that part's not going to produce a 0. But could x squared minus 60x plus 1684 equal 0? I don't really want to try to factor that, so I'm going to use the quadratic formula. So 60, negative 60, plus or minus the square root of b squared. So that's negative 60 squared, minus 4 times a, which is 1, times c, which is 1684. And that gives me a error, so we must have a negative under the square root, so that could never equal 0. So we don't have to worry about where this is undefined. So we're just focusing on where this equals 0. So you square both sides, and I think I'll finish this in the next video. Alright, just kidding, I have a few more minutes left here. Square both sides, we'll get x squared, and then this is x squared minus 60x plus 1684. And then when you square this, you'll get the negative to go away, and you'll have x minus 30 squared. And then this squared would be x squared plus 144. So distributing, we get x to the 4th minus 60x to the 3rd plus 1684. And here we're going to have x squared minus 60x plus 900 times x squared plus 144. Distributing that through, we're going to have x to the 4th minus 60x to the 3rd plus 900x squared plus 144x squared minus 8640x, and then 144 times 900 is 129,600. All right, that's good for now.